Hi friends, a very good evening. Could you please confirm in the chat window if you are able to hear to my voice and if you're able to see my screen clearly so that we know that there are no technical glitches and we can get started in a few minutes. Hear to my voice and if you're able to see. Okay, that's my phone on which I'm looking at the comments. Good. So at least I can see my screen and I can hear to my audio clearly. So please confirm that. Again, I have all of the live chat window on my phone so that I can respond to them. So right now, all these sessions are private sessions. We wanted to do them for the benefit of everyone. But in the coming months, we will surely move to private sessions that will be only for the enrolled students. We want to finish the one iteration of interactive problem solving for all students. From the next iteration, it will all be private, only for the course registered students. Cool, sounds good. Okay, good. So currently we are doing OS. This is the second session of OS. We might need maybe one more session for operating systems. Once we finish that, we'll go to the next set of subjects. Again, this is for today. We'll make an announcement positively by tomorrow or early Monday on the next set of live sessions for the next week. So we try to plan things 1 week in advance because some of the students have been requesting for a general Q&A session. Let's do this. Next week, let's try to finish operating systems with a third live session, which is interactive problem solving. And we'll think of a general Q&A. We can have a theme to the session also. That we'll discuss and let you know, or we can just have a general Q&A to answer as many questions as possible for that students ask. Cool. Okay. Cool. Okay. Any other question? Okay. How many months are required for revision and test series after completing the videos? Again, it is best if you can at least revise 2 or 3 times. If you have made the short notes well, and if you have made, if you're using our detailed notes that we provided, you should be able to revise fairly quickly, number one. Number two, try to at least, again, we have seen a wide spectrum of students. We have even seen students who have finished their preparation late November, even early December and still got good ranks. It all depends on how you are preparing the first time. The very first time when you're learning the concepts, doing practice problems, writing short notes, if you do that properly, revision will be very, very quick and very, very effective. So my recommendation is try to finish the first iteration by early December, but as always, earlier the better. Okay, it's already 7:01, so let's get started with this session itself. Okay, cool. So the session is again the interactive problem solving session of session. This is the second part of operating systems. We will cover a few problems from process management and also a few problems from memory management, right? But we may not be able to cover all of memory management in this session. So we'll have a third session where we'll wrap up with all the other topics. Cool, let's get started now. Again, please try to spend time answering these questions. This is the first question that we have. General questions, you can always email us. We will try and answer as many as possible. So since this is an interactive problem solving session, let's focus on the session itself. Please attempt the questions. Again, this is an easy question. So if you're careful with it, you will be able to solve them comfortably. Again, there are a few easy questions here and a few medium questions. We want students across the spectrum of preparation to enjoy these sessions. So there are some easy questions also here. Again, we intentionally gave slightly easier questions this time because we want people to stay motivated in this game. And nothing is more motivating than solving problems. Of course, there are some medium problems also today. So don't worry. Don't think everything will be easy. There are a few problems that we sprinkled in which are of medium hardness. Okay, thankfully our mentors and other team members are also answering some of the questions in the live chat. Okay, I see many of you have answered the question, so let's wait it out and see. Let's wait for a few more seconds, and then I'll explain the solution. Primarily, people are saying either 18 or 20. Those are the two options that people are giving, right? But think through it. Think through it a little carefully. Okay, so let me explain the solution here. Okay, so we have three processes A, B, and C, right? So the peak demand is 9 resources, 5 resources, and 8 resources. Which of the following is the minimum value of n that will ensure a deadlock won't occur? So in the worst case, let's take the worst case scenario. In the worst case, let's assume 8 resources have already been acquired by process A, 4 resources have already been acquired, 7 resources have already been acquired. Right? So these are already resources that are acquired by process A, B, and C. Now, even if you have one more resource that is still left, look at this. Let's say worst case. Let's take the worst case. We should always think about it from the worst case perspective. In the worst case, let's assume 8 are occupied, 8 are taken up by A, 4 by B, 7 by C. Right? Now, if you have one more resource here, then this one resource can be given to one of these processes, and each of these processes, now let's assume it's given to this process. Let's assume now this process will get all of the resources that it needs. It will complete, it will relinquish or give up the resources, which can be again used by process A and C. So the total number of resources that you need, right, the minimum number of resources you need, that will ensure that deadlock will not occur even in the worst case, is 8 plus 4 plus 7 plus 1. That's 12 plus 19 plus 1, 20. So the answer is 20. And this is a very simple example. I mean, this is a very simple example. Again, I strongly recommend against remembering formulae, right? Somebody is giving this formula of n into k minus 1 plus 1. Again, I don't recommend remembering formulas by heart. I always want you to think from first principles and be able to work it out easily. Of course, there are some places where you should remember formulae by heart. For example, if you want to know the PDF of Gaussian distribution, you should remember this by heart because it's hard to derive it in an examination. But this is more common sense. You don't have to remember formulae for it, right? Again, today as compared to yesterday, we have given more easy questions so that it's more motivating even for students who are not that well prepared. But please understand that we cannot keep doing this because there are also students who are well prepared and we need to cater to their needs and requirements also. Right? Slowly, we'll keep increasing the hardness of problems. Okay, cool. Very good. So let's go to the second question now. Many of you got it right. Okay, so this is a good problem. I think this is one of the good problems of today. This is medium. This is not hard. This is something that you can expect for 2 marks in a GATE exam. Again, please focus on answering the questions because that's the idea behind this session. We will do general sessions where we can discuss general topics. Please try to focus on the problem at hand and try to solve it as best as you can. Again, while you're solving the problem, I don't want to deviate you with some stories or with some miscellaneous stuff. I want you to focus on the problem. This is one of the good problems of today. I really enjoyed solving this myself. Again, please read the question very carefully. Especially this part of the question, please read carefully. I'll put a star mark here. only requires basic arithmetic. Again, this could take a little more time, but that's okay. Try to get it right rather than getting it fast at this point of time. Sorry. Okay, I see few of you putting in your answers. Again, just cross-check your answers once. So, because I'm waiting for others also. Yes, this question is slightly confusing. We have done it intentionally because in the recent past, if you see, questions in GATE are not hard, they're tricky. Okay, I see answers all around the place. 8, 4, 3. Just be careful with your solution. It's basic arithmetic if you're careful. Okay, there is also 4 and 5 options that some of you have given or as potential answers. Okay, I'm waiting for some more answers and hoping that some of you will self-correct your answers. Okay, let's get into the solution since a good chunk of you have put in your answers and some of them certainly are wrong. Okay, let's go and write down the solution, right? So what do we have? We have px plus I with I ranging from 0 to n minus 1. So we have px plus 0, px plus 1, so on so forth, sorry, x plus 1, yes, so on so forth up to p x plus n minus 1. Those are the processes that we have. And it's also given that x is greater than 2, right? And the total number of resources we have are 10, right? We have 10 copies of the resource. Now let's look at this, right? So this process requires x plus I resources. So it requires x plus 0 resources. This requires x plus 1 resources and so on and so forth. This requires x plus n minus 1 resources. Just like in the previous problem that we have seen, imagine, let's look at the worst case always. So let's assume this requires, let's assume this is already holding x minus 1 resources. This is holding x resources and so on and so forth. This is holding x plus n minus 2 resources. Worst case. Just like this, just like what we have seen in the previous problem, right? Imagine this is the worst case, right? And if you have the worst case wherein all of these processes are holding just one less than what they need, you need one more resource now, which can be allocated to any of these processes so that we don't get into a deadlock, right? We want a deadlock free operation, right? So which means the total number of resources that we need is x minus 1 plus x so on and so forth plus x minus n minus 2 plus 1. Now if you sum this whole thing up, what do you get? You can write this as, let's try to simplify this, right? You can write this as n times x minus 1. Look at this, I can take x minus 1 common from all of this. So you'll get n times x minus 1 plus, this is 0. Look at this, plus 0 plus 1, x minus 1 plus 1 is x. So on and so forth up to up to n minus, so okay, till where do we have to do it? We'll have to do it till n minus 2, right? So am I getting it right? We'll have to do it till, so it is n into x minus 1, or we'll have to do it till n minus, so there is one short here, one short here, one short here, so on and so forth. So we'll have to do it till n minus 1 or n minus 3. 1 second. So this becomes 0, this becomes 1. Okay, so okay, so let's write it slightly differently just to avoid confusion, right? So let's write it slightly differently. So this I can write it as, again, just basic arithmetic, right? So let me write it more carefully. Nx minus 1 plus 0 plus 1, so on and so forth. So here I have x plus 0 and I'm getting 1 more than that. So this should be up to n minus 1 plus 1. Let's keep that plus 1 there. Right now, what does this equate to? It equates to n into x minus 1 plus, if you sum up all this, what do you get? Sum of the first n numbers is n into n plus 1 by 2, right? So if you sum up this whole thing, you'll get 1 second, n into n plus 1 by 2. Yeah, so this into n by 2 plus 1. This is what you're getting. And note that your x is greater than 2. Look at this here. So what do we want to find? We know that this has to be less than equal to 10 because we are told that the maximum number of copies we have is 10. Right? So that's what we already know. So if this whole expression has to be less than 10, remember that we want to take the minimum x value here. Because as x keeps increasing, this whole value will keep increasing. Right? So we want to take the minimum possible value of x. Right? Note that x is an integer and x is greater than 2. Which means the minimum value of x that you can get equals to 3. So let's plug in the 3 here. So then what do you get? You get 2n plus, you get n minus 1 into n by 2 plus 1 is less than equal to 10. This is what you get, right? Now let's simplify this expression now, right? Again, I'm trying to use the same page here. If I try to simplify this whole expression now, what will I get here? I'll get 4n plus, right? 4n plus, where am I here? Okay, let me be a little careful so that I don't do mistakes. 4n plus n minus 1 into n, right? So it is n minus 1 into n plus 2, right? So I have plus 2. So I have n minus 1 into 2. This 2 gets multiplied here. Plus 2 is less than equal to, so this 2 goes that side, is less than equal to 20. This is the expression that I'll get, right? So now what happens? So now let's try to simplify this. If I take this 2 that side, I'll get 18 here. So what do I have? I have 4n plus n square minus n is less than equal to 18. This is what I have. This I can further simplify it as n square plus 3n is less than equal to 18. Which means n into n plus 3 is less than equal to 18. Right? This is what I want, right? So did I get everything right? Okay. Okay, so yes. Now remember that n also has to be an integer. Now imagine if n equals to 3. What happens if n equals to 3? If n equals to 3, this becomes 3 into 6, which is less than equal to 16. It's working out. We want, what is the question? The maximum possible value of n. Now if n equals to 4, what happens? You get 4 into 7, which is 28, which is not less than 18. So the minimum or the maximum value of n that satisfies this equation is n equals to 3. The maximum value of n that satisfies this. So the answer here is 3. Right? So the question itself is a combination of two things. That's why we rated it as medium. First, this concept itself is straightforward. Right? This concept of each process holding just one less than what is needed is a very simple concept. Then you get this whole expression. The tricky part here is solving this expression very, very carefully while keeping in mind that x has to be greater than 2 and recognizing that x is an integer. So the minimum value of x that you can have here is 3, and as x increases, this whole thing will increase, but we don't want it to increase because we want it to be less than 10. We want the maximum value of n, right? So we will take the minimum value of x so that we can get the maximum value of n. That's the whole idea, right? Again, this is all basic engineering mathematics. I can call it 11th class mathematics, right? So this is a combination of concepts from your engineering mathematics or basic high school or 11th, 12th class mathematics and the concepts of operating systems. This was one of the fun problems that I solved when I was solving it today, right? Okay, let's go to the next question now. Oh, this is also a good question. It's easy if you know the concepts of resource allocation graphs. This is easy. By gate standard, this is easy, but it's a good question. Just be careful with the diagrams. They're simple if you're careful. Okay, I see people putting in your answers. Good, good, good. Again, most of these questions, the way we work out is our team sets the question paper, a team of mentors. I try to solve it beforehand on my own. Most often I get it right, but once in a while I also fall for a silly mistake. So it's okay if you're making a silly mistake here and there, just learn from it, and that will be helpful for you, right? It's okay to make one odd silly mistake here, but if you have to revise. Again, to be honest with you, when we start a subject, I take up our notes, I revise the subject before I start solving it, because it's impossible to keep track of so many subjects and be great at everything. So before I take up any of these live sessions, I revise it from our own notes, and take this test just like any of you. Okay, I see good answers. Mostly people are saying A or C. Those are the two options I see. Okay, just be careful with your answers. Again, the interesting part here is that you have resources which are multi-instance, like this and this. These are resources which are multi-instance. This is a resource with a single instance, right? So this is a resource with multi-instance. That's what you have to be careful about. Okay, let's solve this. This is a fairly straightforward question. A very common mistake that many people make is if there is a cycle, they'll simply say that there is a deadlock, right? This is something that is there in many people's misconception. This is not always true. If you only have single instance resources, this statement is true. But when you have multi-instance resources, cycle is a necessary condition, but not a sufficient condition for a deadlock when you have multi-instance resources. That's the catch here. The reason many of you answered C probably is because you said, okay, there is a cycle here. Okay, there is a cycle here. Oh, there is also a cycle here. Oh, so it must be deadlocks in both cases. But it's not so. That's true if you have single instance resources. But when you have multi-instance resources, it's not always true. For example, let's look at this. There is this cycle, right? P1, R1, P2, R3. Okay, so there is this, there is this, there is this. Okay, so there is this whole cycle here. But look at in addition to the cycle here, look at this. P2 is waiting for P3 to give up this resource. P3 is waiting for P2 to give up this resource. It's also waiting for P1 to give up this resource. And P1 is waiting on P2, P2 is waiting on P3. So all of them are in a deadlock situation now. So this situation is surely a deadlock case, right? But if you look at this is not a deadlock case. The reason being, look at this. P1 is requesting for a resource here. See, there is also a cycle here. If you notice, there is a cycle here. But cycle doesn't mean deadlock when you have multi-instance resources. So this is surely deadlock. Okay, let me write a D here. In this case, it did not be a deadlock. I'll tell you why. Look at this. You have this resource that is being used by P2. Now P2 will use this resource for a while, and once it is done, it is not requesting any other resources. Once it is done, it will give up that resource. Now this resource can be taken up by P1, right? Which means P1 need not wait for P3 to give up this resource. P1 can just wait on P2 to give up this resource and then it can take it up. Similarly, look at this P4 here. P4 has this resource and P3 is waiting for this resource. So P3 and P4 don't have any dependency. So P3 will use this resource for a while and give it up. Once it gives up, this resource can be given to P3, right? So in this situation, you are not in a deadlock. So this is not a deadlock case. Again, this is a very small detail here, that if you have single instance resources, then then a cycle basically means you are in a deadlock. If you have multi-instance resources, need not always be true, right? In other words, cycle is necessary but not sufficient for a deadlock to occur. So the right answer here is A, because only one is in deadlock, not two, right? Very simple. Cool. Okay, let's go to the next question now. Okay, so this is the next question, right? Yeah. Again, for the previous problem, there is also a wait for graph that you can draw and argue. That's another way of solving. There are multiple ways sometimes to solve the same question, right? I won't call this fourth problem a medium problem because it's actually easy. If you're slightly careful with it, if you know about safe sequences, this is more or less straightforward. So if you know the concept of safe sequence, this is more or less straightforward. Okay, people are putting in your answers, A, B. Okay, let's see. There is also a C option that somebody is suggesting. Okay, good. I see a lot of people making silly mistakes who answer early. That's something that I've been observing. People who are answering in a hurry are committing more silly mistakes because I see answers that are coming in slightly later tend to be more accurate in general. So that's a good sign that you should be careful with solving the problem and not be in a hurry right now. Your speed will automatically improve. Gate is most of the times not about speed, it's about getting answers correct. Okay, since a good chunk of you have answered, so let me go into it, right? So we have a total of 12 units. This is important data point. And okay, we have 4 processes. This is used, this is maximum. And how many more could be needed? Let's also fill that up. So 5 are already being used, max is 8, so the need is 3. The need here is 2, the need here is 2, the need here is 4. right? So that's the need. Now, if you know the need, so remember, we have 12 units. How many have already been taken up? 5 plus 5. So 10 have already been taken up. So we have a total of 12 units, of which 10 have already been taken up. So we are left with 2 more units, or two more instances of the resource that we can allocate. Now, let's see. We have 2 more instances, right? Which means we cannot schedule in a safe sequence. We can't add P1 or P4 because they need more than 2 resources. Right? So in your safe sequence, P1 or P4 can't be the first process. So obviously this will rule out A and D. Simple. Let's start eliminating options. That's sometimes faster. Okay. Now let's look at option. Okay. So this is one part. Let's look at option B now. What does option B say? Option B says let's give it to P2. Okay. Imagine if I allocate these resources to P2. Okay. Now what happens? P2 will take these 2 resources. So P2 gets the 2 resources. Right, P2 gets the 2 resources. P2, let's assume, completes it executes the whole thing, right? Then it will release all the 3 resources. So okay, so then it releases 3 resources. Now I have 3 resources now. So because I have 3 resources, I can obviously execute P1 after P2, right? I can obviously execute P1. I can also execute P3, by the way. But let's look at this option. P1 followed by P2 followed by P1, P2 followed by P4. Look at this. Now I have 3 resources. These 3 resources I can either give it to process 1 or I can give it to process 3. I can't give it to process 4 because process 4 requires 4 resources. So obviously this is incorrect. This is incorrect. This is incorrect. This is incorrect. See, we are ruling out options as we are solving it. So P2 followed by P1. Okay, so if I give it to P1 now, so let's assume these 3 resources are given to P1. P1 will get the maximum resources that it wants. Then it will give up all the 8 resources. Those 8 resources can be taken up by P4 and P3 in any order. Doesn't matter. Because this requires 2 resources, this requires 4 resources. So B seems to be a reasonable, B is one of the safe sequences. Certainly A, C, D are not. So B is the right answer here. Again, this is a fairly straightforward problem. It's just borderline medium. It's actually easy. The reason it is medium is because some people may forget about the concept of safe sequence and how to determine this. Most of operating systems is common sense. Okay, it's very commonsensical if you know the concepts. If you don't know the concepts, it's Greek and Latin. Okay, cool. So let's go to the next question now. Okay, this is an easy problem. Okay, please be careful. Please read this carefully. There is a small twist in this question. It is easy, but there is a small twist. You have to be careful with that. This is a typical type of question that you can expect because this looks very easy, but there is a small trick. If you're not careful, you'll fall for it. It's a small boundary case that you have to be careful with. Many of you are making a mistake. Many of you have started putting your answer. So many of you are making a mistake. Please look into it. There is a very subtle detail that is you have to be careful with. Questions like this are often given in GATE to fool or to make sure that 99% of students make a mistake here. That's the whole purpose they give questions like this. Because they want you to think of boundary cases. Okay, I see all the answers A, B, C. So think through it carefully. Okay. There is a little trick here. Again, I observed this pattern earlier also. As people may take more time and think through the question carefully, they are answering more accurately. So instead of being in a hurry, please think through it. Speed is not important here. That's why I even stopped the timer, because timer was pressurizing students to answer fast. I'm just going with whenever enough number of students put in the answers, I would just jump into the solution. Okay, so let me explain the solution. We have 5 processes, P1, P2, P3, P4, P5, right? That's cool. Now, some of them are single threaded, some of them are multi-threaded. All these details are given just to confuse you, to be honest, okay? Now, how many page tables will be managed by the operating system if all the page tables are always in the main memory, right? Now, remember, one thing that you have to be careful about is, let's take a process like this. Let's look at process 3. Process 3 has 4 threads, right? Threads share the same memory space. That's very important. The fundamental principle of a thread is all the threads in the same process, all the four threads share the same memory space, which means they share the page table also. If they were not sharing the page table, the context switch will become just very, very cumbersome, right? So the whole objective of having multi-threading is you share the memory, you share the same memory, all the 4 threads share the memory so that you can context switch faster. Because they share the same memory, they also share the same page table. So they also share the same page table, right? So obviously many of you have started saying exactly 5. Your argument probably is there will be one page table for this, there will be one page table for this, there will be one page table, there will be one page table, there will be one page table for this. So there are exactly 5 page tables. That is true if you have single level paging, right? So if you have single level paging, you're right. If you have single level paging, the operating system has to exactly manage only 5 paging tables. But nobody told you that there is only single level paging. You could have multi-level paging also. In multi-level or hierarchical paging, some pages or some page tables, some page tables will be in memory. Some page tables could be in the swap space, right? So at least 5 is the right answer, right? Look at this. Again, this is the boundary case that you have to be careful about. Many people have answered 5 because you thought, okay, you got the core logic of the threads sharing the memory, all of that stuff. But nobody told you that this system is a single level paging system. It could be multi-level paging. And you should think of this case because there is this option. If this option wasn't there, that's a different case. But because this option is there, if you have multi-level paging, right, then you can have multiple page tables, one page table at multiple hierarchies. So you could have more than 5, right? It's a very catchy question, and we are seeing more and more of these. This question could be just 1 mark, but I think 99% of the people will make a mistake here. And when I was solving this, I got triggered as soon as I saw this option. Initially, I was thinking, makes sense, there should be 5. But I read through all the 4 options. I saw at least 5. Then I started thinking, why did somebody give this option in the first place? Right? Then it took me a second to realize that there is also multi-level paging. We always by default assume single level paging, but we should not, right? So cool. Very good. So let's go to the next question. This is also a very simple problem. This is about if you know the next fit allocation system, this is straightforward. Again, for those of you who may have forgotten what is next fit is very similar to first fit, except that you will only start looking from where you left off in the previous allocation, if you have forgotten that. This is a very easy problem. You can think of it as a good revision question. Again, sometimes you might encounter a question like this for 1 mark in GATE. If you know how next fit works, this is very simple problem. Again, most of you have started putting in your answers. Good, good, good. Again, we have only been giving slightly easier questions so that students' motivation levels are in a reasonable level, but please do understand that the actual GATE questions will be harder than simple questions like this. But we hope this will help you build confidence and also help you in a revision-like strategy, right? Again, our practice problems are in our course, and the test series will certainly be at most of them will be at a medium level. There are a few easy ones there, but tricky ones. Okay, cool. So most of you got it right. So let's get into the solution itself, right? It's very simple. So what do we have? We have these 10 MB, 4 MB, blah blah blah. We have the request 12 MB. So let's assume we start here, right? So we start here. This doesn't fit. Then we go here. It doesn't fit. We fill the 12 MB here, right? We fill the 12 MB here, right? Cool. So this went through. In the next fit, what happens is this was the last thing that we saw. So we continue from here. It is very similar to the first fit, but every time instead of starting from the very beginning, we continue where we left off in the previous allocation, right? So next comes 10 MB. So we look here. So this anyway, 10 MB will fit here, right? 10 MB will fit here for sure, right? So 10 MB is allocated here. Then you get 9 MB, right? So the 9 MB, again, because it's next fit, we will continue where we left off last time. So 9 MB will try to be fit here. It can't fit. So 9 MB will fit here exactly. It will exactly fit into this hole, right? So what is the question? Which hole will be allocated for the third request? So for the 9 MB request, which hole is allocated? 9 MB hole is allocated, which means none of this is the right answer. It's a very simple question. If you know the next fit algorithm, this is simply straightforward, right? Cool. Let's get into it. Let's get into it. Okay. Again, some of our practice tests in the subjects are also freely available so that students can look it up and see the quality of questions we ask. We intentionally kept a few practice tests in our courses also open to everyone, even to non-course registered students. Today we are giving slightly easier questions so as to help everybody stay motivated, but we'll mix up few easy, few medium as we keep going. And as we come closer to the examination, there will be more and more of medium questions, few hard and few easy. Again, if you know the basic concepts of internal fragmentation and the best fit algorithm, it is straightforward. Just make sure you recognize that we have to use best fit and we have to compute internal fragmentation. Again, please be careful to read this in the order of arrival. This is something that many people may miss out. This is a fairly straightforward question. We'll solve slightly harder questions in the next iteration with page tables and things like that. There are a lot of interesting problems in operating systems around page tables. It's a very interesting topic. Okay, most of you have put in your answers and most of your answers are correct. The right answer is 754 and it's very simple. Look at this. So first we have job A, which requires 256 KB, which means job A of 256 KB will be allocated here. So what is left out here? 44 KB, right? Then you get job B, which is 900 KB. So where will you assign it? You will assign the 900 KB here, which means you will be left with 0 KB of fragmentation or internal fragmentation to be precise. Okay, so job A, job B are done. Job C is 50 KB. Only here you can fit it, which means the internal fragmentation will be 150 kilobytes. Next you have the 350 KB, right? The 350 KB will go in here, right? So which means 910 minus 350 is 560, right? So if you sum up all of this, you will get 754. I've already done this math earlier when I was solving it before the session, right? So very simple question. It's also very easy. If you know the best fit algorithm and if you know about internal fragmentation, this is simple and straightforward, right? Cool. Let's go to the next question now. Sorry. This is also, I don't want to even call it easy. It's actually trivial. Sorry, some people are saying, please only give easy questions. Then you will never be able to crack GATE. Let's be realistic here. We want to give a few easy questions here and there so that your motivation levels are high. If you do not give medium level problems, you will simply never crack GATE. You live in a bubble that you're good, which you're not if you cannot solve medium level problems. This is, wow, people are getting it incorrect also. Wow. Okay. Come on guys, this is very, very simple. Again, Lakshmidhar is saying, please don't include easy questions. Again, please understand that we have to make trade-offs because we want to help students across the spectrum, across the levels of preparation, right? So because this is easy, next time it will be slightly on the medium side. We will not do hard. It will be very similar to the yesterday's session. So we'll do one session slightly on the easier side, one session slightly on the medium side, one session slightly easy, one session medium. But in the next iteration, please don't expect these many easy questions. You will do more and more medium level questions. I completely understand. There are students across the spectrum and we have to do, these are public sessions, right? Again, those of you who want more interesting questions, we anyway have our practice tests, we have our mock tests, we have a test series where you'll see way more interesting problems. So we're trying to balance it out. Yesterday was I enjoyed yesterday's session, to be honest with you. Those problems are like what you would really expect in GATE. This session is slightly watered down because there are more easy questions. Okay, I see people putting in your answers, so let's answer it, right? I thought this was trivial, not even easy. The number of entries in the page table is equal to the number of frames. No, never, right? The number of entries in a page table is equal to the number of pages that are being used by the process, not the number of frames that you have. So obviously this is incorrect. Next, a page table entry may contain information related to multiple pages. No, a page table entry contains information only about one page, right? Because what is a page table entry? What do you have? You have the frame number and some additional or auxiliary bits, You have some additional bits like dirty bit, read write bits, all of that stuff, right? So a page table entry, which means one entry into the page table, will only contain information about one page and not about multiple pages. So this is also incorrect. So obviously D is the right answer, right? Because none of them, both of them are correct. No. So D is the right answer here, right? So let's go to the next question now. This is a slightly, again, this is the type of question that you typically see in GATE. In GATE, you'll see a lot of medium level problems. I think less than 5% hard questions and a few easy questions. But a good chunk of questions in GATE will be medium level. Okay, people are putting in their answers. I'm also writing something to explain after this question is answered by you. Okay, many of you are putting in your answers. Good. I think many of you got it right. I think one or two of you got it slightly incorrect. Okay, we'll solve this problem, or else I'll explain this and then we'll solve the problem. I'll explain what I wrote just after I answer this question. Okay, let me explain the solution. This is fairly straightforward. You have a computer which has 1024 pages in their address space. Processes that have 1024 pages in their address spaces, keeps in the page table in memory. Cool, all that is cool. Okay, so let's look at the whole thing. So if you have a virtual address, how does it work? You have to know this diagram. Well, the moment you know this diagram, all of operating systems is easy. So virtual address has the page table and the offset, right? Let's write it as offset. Now this page table, so how does your TLB work? It's just a buffer basically. Your TLB is a very fast buffer, right? So you have your TLB here. So first this page table will be looked up in the TLB. If it's available in the TLB, you get a TLB hit, right? So if you get a hit, it's very simple. So if you get a hit, the physical address, right? Let's assume it has a frame number and offset. The frame number will come from here. But if it has a miss, which means the page number that we are looking for is not present here, then it goes to the original page table, right? It goes to the original page table. Obviously, it will be present in the original page table. So in case of a miss, In case of a TLB miss, the data from the page table, or basically the information from the page table or the frame number from here, is used to fill up your physical address. This is the whole logic, right? If you know this logic, this problem is very, very simple. Okay, so let's look at this. Your TLB is a buffer which takes 100 milliseconds, right? This takes about it says 100 nanoseconds, I'm sorry. Yeah, milliseconds make no sense. It should be nanoseconds, right? So this takes 100 nanoseconds. This takes about 500 nanoseconds. And what we want is a 200 nanoseconds. The question is all about what should be the hit rate. Let's assume the hit rate is R. Okay, then what do we want? We want 200 to be equal to, whenever I have a hit, look at this, whenever I have a TLB hit, what is the total time it is taking? It's only taking 100 nanoseconds, right? So it's taking 100 nanoseconds. Plus, if there is a miss, right, what is the probability of, so if R is the hit rate, the miss rate is 1 minus R. So when there is a miss, what happens? You have already checked in the TLB once. So you should use this 100 nanoseconds plus this 500 nanoseconds. So the total time to construct your physical address in case of this is 100 plus 500 nanoseconds, right? So this whole thing, so if you simplify this, what do you get? You get 200 equals to, so you have 100 R plus 600 minus 600 R, all right? So this is what you have. So what will this be equal to? So if you start moving around, you get 400 on this side, you get 500 R. So R is 4 by 5, which is equals to 0.80, because we want up to 2 decimal places. Very simple, right? So if you know how TLB works, the concept of TLB hit and miss, this is a very, very standard, simple problem. Oftentimes we've seen that problems like this could be even asked for 1 mark in GATE because they're so straightforward, right? So one thing that I wanted to tell you was, so since this is the first iteration, let's agree to a middle ground so that students across the spectrum are happy with it. So let's do one thing. So we will first, in this first iteration, we'll do 5 easy problems and 5 medium problems, right? From the next session onwards. In the second iteration, we'll do 3 easy, 6 medium and 1 hard. Again, we still don't want to do hard problems because we'll do it in the third iteration. We are hoping that we can go through all the 3 iterations before the actual exams, right? So in the third iteration, you will have 7 medium and 3 hard. And the 3 hard also will be hard because they're actually medium with some trickiness. There is no point in doing very hard questions because they'll never be asked in GATE. The people who set the GATE question paper are also sensible people who know that asking just hard questions for the sake of asking hard questions is not helpful, right? So since this is the first iteration, we will focus on 5 easy and 5 medium now, so that people who are well prepared, people who are not yet well prepared, both of them can be happy. This is like a middle ground that we'll do. Again, second and third iterations will only be accessible to our course enrolled students. Okay, let's get moving now. So, we have only one more question, right? So we have also 4 or 5 minutes. Again, this is a simple question. So somebody is asking about explaining TLB. Again, I think we have done a decent job in explaining TLB in our course videos with tons of examples. If there is something that is not clear from there, please shoot an email and we will surely respond back. I think because we don't know exactly what your confusion is. If you have a conceptual doubt, please email us and we'll try to resolve it, obviously with a first preference to our course enrolled students. This is a simple question. Many of you are getting it right. There is one very interesting question that somebody asked. I'll answer that also. Because there are so many easy questions, we get more time to answer some general stuff. I'll write the question here. It's a good question. If you're a course enrolled student and if you have any conceptual doubt, please don't hesitate letting us know. We will give you more examples, we'll explain it more. Whatever is your point of confusion, please reach out to us. We want you to reach out to us if you have a problem. Okay, very good. Most of you actually got it right. So let me answer that. And there is also a very interesting question by some of you. I'll also answer that after I solve this problem, right? Many of you got it right. Cool. So, okay. So 128 MB is the physical address space, right? Which means your physical address itself is going to be 2 power 20 plus 7. So 2 power 27. So your whole physical address space itself is going to be 27 bits, right? So this whole thing is, let's say, 27 bits, right? This will have obviously the frame and the offset, right? The frame ID or the frame number and offset, right? Now, what else do we have? We are given that the page size is 4 KB, right? That's the page size, which means a page itself is 4 KB, which means this is 2 power 10 and this is 2. So this is 2 power 12. Which means the offset itself requires 12 bits, because if the size of each page itself is 4 KB, then we need 12 bits to address. So the offset itself, again, since nothing is given, we assume that it is byte addressable. We are not given anywhere that one word is 2 bytes or 4 bytes. Nothing is given. So the default assumption should always be byte addressable unless given otherwise, right? So 12 bits go in the offset. So how many bits are left here? 15 bits are left here. Okay, cool. So this is good. Now, what is the question asking us? The page table entry is 4 bytes, right? If you have a page table, what all stuff is there in the page table? You have the frame number, right? You have the frame number and you have some additional bits, right? Dirty bits, read write bits, all of that stuff, right? So what is the question asking us? Okay, the number of bits available to store additional information other than the frame number. Page table entry size is 4 bytes. Okay, so 4 bytes basically means 32 bits. So this width itself is 32 bits, right? So this width itself is 32 bits, right? And the frame number itself, to store the frame ID or the frame number, we need 15 bits. So 15 bits go away here. So what is left here? 17 bits are left here. So the question is saying how many bits are available for additional or other information? 17 bits. Done. Problem solved. So very good question that I think Ion asked, and also someone else mentioned that it's their concern. Because this time the competition could be severe. Can we expect a paper like 2006 or 2003? If I have to make a guess, again, I could be wrong here. If I have to make a guess, I think it will be no. The reason being, I think the people who set the question paper in 2006 and 2003, I told you this, right? 2006 topper. In those days, because I wrote this paper myself, AR1 I think got about just under 50 marks out of 150 marks, because he was 1 year senior to me at IISc, right? So they realized that having such a very hard paper is harder for them to distinguish between, because just giving a hard paper is very easy for a professor at IISc or IIT. It's very easy for them to give a hard paper, but the difference between a good candidate and not so good candidate will also be harder to distinguish, right? Because the top marks itself are so low. If you notice a pattern that GATE has moved to in the last 5 to 6 years, they're going more towards tricky questions, interesting questions where people make mistakes, and there are very few hard questions. So my gut feel is GATE will stick to the same pattern. They might have slightly more harder questions than the last 3-4 years, but it will not be as hard as 2003, 2006. That's why when I mentioned a while ago, we will do a few hard questions in the second and third iterations just to prepare for the worst case. It's always good to prepare for the worst case. And remember, your competition is not with the question paper. Your competition is with other students. If you have prepared well and if it is hard for you, it's hard for everyone. I told you, right, in 2006, GATE AR1, my 1 year senior at IISc, he got just, I think, 49 or 50 marks, just under 50 marks out of 150 marks. That's like in today's paper, it's like getting 33, 34 marks out of 100 marks. Just imagine, I mean, last year, I think the top marks were around 80-ish. right? So I think the people who set the GATE question paper learned that setting just really hard questions is not helpful, but setting tricky questions could be helpful to rank students better, because that's what they are in. They want to rank students to take them into graduate programs, right? But it's helpful to prepare for the worst case, but don't panic about the worst case. Just don't worry about it. I did not prepare for the 2006 question paper expecting it to be hard, but I did a decent job at it. Okay, sounds good, folks. Thank you very much. And from next time, as I just mentioned, let's do 5 easy and 5 medium. Of course, some of the easy also can be tricky. Some of the medium also can be tricky, right? So I think this is a good balance in the first iteration. In the future iterations, we'll also have more and more of medium questions and a few hard questions sprinkled here and there. Thank you very much, and see you next week. We will continue on operating systems, and probably we'll do a general live session next week. And then we'll start with the next subject. Cool. Thank you very much, folks. Bye-bye. Have a good night, and please stay safe.